Hello, today we're going to talk about nuclear reactions. Alright, when you have a nuclear reaction, you have to balance nuclear equations. So, in a nuclear equation, you have transmutation, which is the change of one chemical element into another by nuclear decay or bombardment. What this means is the nucleus lets out an alpha, beta, or gamma ray. So an alpha particle, remember, is a helium atom. So you're getting rid of 2 protons, an atomic mass of 4. A beta particle lets off what resembles an electron, so you lose 1 proton in that case, but the mass is the same. When you get rid of a gamma ray, you don't get rid of anything because it has no mass. There's no protons, there's no neutrons, no electrons. But we're actually not going to talk about the gamma ray when balancing the equation. We're only talking about alpha and beta particle decay. So just to review, say I have uranium 238. All right, so how I write this in the isotope format is 238, and its atomic number is 92. I remember, so U. All right, so say there is an alpha decay here. Alpha decay. So in an alpha decay, you're going to lose a helium atom. All right? So you have 2 protons and you're losing 4 from your atomic mass. Now what this becomes, because you're losing protons, and protons is how you identify an atom. So if uranium loses 2 protons, it's no longer uranium, it becomes something else. In this case, it becomes thorium, which is that, which has an atomic mass, in this case of 234, an atomic number of 90. So to have a balanced nuclear equation, these have to equal each other. So 90 plus 2 has to equal 92. And it does. Our atomic masses have to add up too. So 234 plus 4 has to equal 238. All right. Now this over here, the uranium, is called, I'm going to switch colors because I haven't used red today. It's called the parent function. Not the parent function. Sorry. That's math. It's the parent element. This, the thorium, is the daughter element. I have no idea why it's called that. So just, and this is whatever the decay is. So in this case, it's an alpha decay. We'll talk about beta decays in a second. So you just have to make sure those are all balanced when you do it. All right, here's our first example. So thorium releases a beta particle. So thorium has an atomic mass of 234, and an atomic number of 90, and you're doing a beta decay. All right, so if it's a beta decay, what you're releasing is what looks like an electron. All right. So what we're asking for here is what is the new element? All right, so we have to figure it out. So thorium has a beta decay, or loses a beta particle. So you're losing no mass. So these have to equal it up, correct? So 234, if you want to write it as an equation, you could say this is x plus 0 equals 234. So if you solve, x will have to equal 234. Same thing down here with the atomic number. I could say z plus a -1 equals 90. Add 1 to both sides. So 91 is going to equal the z. So now you go to your periodic table and figure out what 91 is, and it's protactinium, or PA. So there you go. So now it's balanced. So if I switch this to 234 over 91 protactinium, however you say it. So 234 plus 0 is 234, 91 minus 1 is 90. And there you go. That is how you balance a nuclear equation. We're going to do another one now. All right, so next one, alpha decay of radon Randell 222. So we do 222, which is our mass, and its atomic number is 86. If you don't know its atomic number, like I didn't, then I had to go and look it up. All right, and it's releasing, it's an alpha decay, so that's 4 to a helium atom. So what do we start with over here? A, Z, and our box. So I'm just gonna keep with this equation thing. So A plus 4 has got to equal 222. Subtract 4 from both sides, and I get 218 equals A. All right? So 218 plus 4 does equal 222. Now let's start down here at the bottom. Next, so Z plus 2 is going to equal 86. Subtract 2 from both sides. Z equals 84. So we look at our periodic table and we figure out what's 84, and that's I really need to get better at pronouncing names. Polonium, like colonium, but with a P. Polonium. And that is correct. So what you really have to remember here is what are you getting rid of? If you're getting rid of alpha particle, it's going to be a helium atom. If it's a beta, then you're going to get rid of just one of the atomic mass. Or the atomic number, not the atomic mass. That was my fault there. The last thing, I'm just going to read this definition off. Half-life is the time it takes for 1/2 of the atom in a sample to decay. So uranium-238's half-life is 4.5 billion years to decrease radioactivity by 50%. So if you had, so just half it by its time. All right, so if your half-life is a day, every day it's going down by half. So after 4 days, if you have 100 of a sample, it'll be like 6% left of it. All right, so half it, so 100 to 50 to 25 to 12.5 to 6.125 and so on and so forth. That's how you half-life it. All right, this has been Nuclear Reactions. Hope it helped. Good luck.